As you all know, I think the assignment came out on the weekend, on Saturday. That's your first assignment. And the first deliverable is due on Sunday. This Sunday. It was a one-day extension because we stuffed around a bit releasing the assignment. We had troubles getting onto the CSC website for a day. So please do make sure you've read the assignment and thought about it before going to your tube. And if your tube's at the end of the week, make sure you've started it before going to your tube. And if you look at the assignment, you'll see you do it with your presentation partner. So make sure you get in touch with them and start your planning because it's due on that one. Now, when I was planning today's lecture, I thought, oh, last week, in that last lecture, there was something I meant to say, but I couldn't remember how much detail I went into it on. So I thought, oh, that's easy. That's from last week, because if you remember, one group of students each week is responsible for writing a transcription of the lecture, so you can see what was covered. And what I found was 16 individual pages, most of them blank, some of them containing a handful of bullet points, which is terrible. So I thought, well, maybe it's my fault. Maybe I haven't made clear to you what we would like the raw notes to be like. What we'd like the raw notes to be is a faithful transcription of what happens in the lecture, ideally from several different points of view, so people who miss a lecture or just forget what happened in the lecture can go and look at them and refresh their minds. The sort of notes you wish that you had for every single lecture, so you could miss some perhaps, in this course you can have, and you only need to write them once because we're all doing it collaboratively and sharing them. So I would imagine in every tutorial you'll say, let's divide into 4 groups. Maybe one group is in charge of the first half hour, one group's in charge of the second half hour, one group's in charge of the third half hour, and one group's in charge of the fourth half hour, and then you all take very detailed notes for those half hours and type them in and put them up. Now, rather than marking the week 2 ones, because it was nice to see that people had started, but it would definitely be a fail, a clear fail. Rather than marking them, I'll just leave them for another week. So these guys have another week to put them up. But those that are taking notes today, who are those in David's Wednesday class, please make sure you put very detailed notes up immediately after the lecture or as quickly as possible after. Now, because of that, I'm afraid we're destined to repeat last week's lectures exactly again. Or skip a huge amount. We'll see what happens. Last year, this book here, let me turn on the light so you can see it. This book here is the... can you see that? This is the textbook from the course last year. The students wrote these notes. These are what we call the study notes, which are based on the raw notes, but with explanations and things added. Not just a transcription, but with an expansion. Everyone put it together. It's this huge, fantastic set of notes. I'll put an online link to them if you want, so you can see the notes. When I say last year, it was last year in the first course, 1917. But here's just like a transcription of the whole course with tips and hints and all the exercises and all the hard things. I printed this out for them, and they all had it in the exam. This was the textbook that they wrote. And then they took it at the end of the course to remind them of what they were in their old age. So you guys will be doing this too. So do make sure, whenever you feel like writing something, someone's already done it, good on you, whoever it was, they put the exponential notes up, or the log notes. They couldn't remember exactly how logs work. So they put it up in the study notes. Instantly it's appeared in the textbook. If you click on the link to this textbook, you'll see it's appeared there. Now it will be printed out and you'll have it in your final exam. So do make sure you take good use of that and write down any notes you think about as you go. Yes? Well, where does it say whose turn it is? We go through the tutorials in chronological order. So let me just go to the schedule. Oh, it's hard to travel around here. The schedule. Turn this off. Am I on the schedule now? Oh. Yeah. Oh, this is the course homepage. Looks suspiciously similar to all the other pages. You only see the header, but if you look down below, you'll see here's the course homepage. Zoomed in frontingly. Let's zoom out a bit. No, maybe that. Let's zoom out a bit. No? There we go. Here's the course homepage. If you click onto the when and where, you'll see for each week, let me make it even smaller. You'll see for each week is the name of your tube class and who's doing the raw notes duty that week. So the ones doing raw notes duty this week are the class Wednesday 12A, which is David's Wednesday tube. Wave at me if you're in David's Wednesday tube. Cool. Do you want to even do it as simply as saying, in case you haven't planned it amongst yourselves already, this side do the first lecture, this side do the second? Does that sound like a good plan? So this side do the first half, this side do the second. How about that? You know. Did you have a quick? Oh, thank you. Thank you. Let me just plug myself in. So that's the end of all the admin. Are there any questions before we start talking about non-admin? Any sort of admin-related questions? Does anyone know how to open something? It's child-proof. Does anyone have a hammer? Oh, hang on.
The batteries are already sweating.
Ta-da! Okay, we're done. Were there any questions? Wave at me. Is everyone enjoying uni so far? Week 3? Woohoo! Yes, excellent. Good to see. Well done, guys. Uni is fun. And it's a great chance to learn stuff. It's a smorgasbord. Learn as much as you can while you can. Okay, let's go schedule. Reasoning about algorithms, that's today. Lecture slides, that's us. And I put it in the admin only section. I don't really know why I did that. I'll stop that. Normally I'll try and put it up where you can see it straight away. Okay, let's go. So information and Claude Shannon. So I've mentioned Claude Shannon before, an amazingly smart American. I think he was a professor at MIT. Certainly he did his undergrad at MIT. A really brilliant guy. Around the time of the war, made all sorts of really important contributions. The Americans would probably regard him as the founder of computing, in the same way the Brits would probably regard Turing as the founder of computing. He's an astonishingly clever guy that every time he published something, it started a whole new field and invented all sorts of wonderful new things. But the reason we're talking about him today is that he was really the person that started this notion of information theory. And information theory is an appropriate point to start today's lecture, because if you remember, last week's last lecture, we finished with this n log n barrier. Do you remember that? We were looking at sort algorithms, we've been classifying them, thinking about what it means to have a complexity and so on and so on. And we noticed that any algorithm to sort things who worked by comparing elements, pairwise comparing of elements, not necessarily adjacent elements. That was our inversion barrier that we had to first break, but just comparing a pair of elements, necessarily ran into this barrier we called the n log n barrier. And do you remember it was an information barrier? Does anyone remember how the barrier works? The reasoning that it's very hard to break n log n? It's such an easy question, you're looking for the hard question hidden in that question I just asked you. So, no, I just mean the easiest thing of all, just the notion of how much information is there in a permutation of n things. If I've got n things that I want to sort, that means coming in I have some permutation of the sorted arrangement, and coming out I've got the sorted arrangement. How many different possible inputs are there if I've got n items? There's n factorial of them, that's right. So the amount of information, you would say, to describe the sorting process needs to be able to do different things depending on the input it gets and ultimately sort it. So it needs to be able to do at least n factorial different things, because it can have n factorial different inputs. So it has to have n factorial different execution traces, if you want to think about it, through the algorithm. So how can a program have a different execution trace? Well, it's when it does a test. When it executes an if statement or a while statement, when it evaluates a test, depending on the result of the test, it'll either go here or here. So this is the only way we really have in a program of splitting into a pair of execution traces from a single one. So if we need to have n factorial execution traces, how many splits do we have to be able to be sure at the end we've split into at least n factorial things? And we looked at that problem, do you remember? I'll just do it again quickly on the board. Every time we ask a question, we split. If we ask one question,
we have two possible traces. If we after asking the first question, if we asked a second question, then conceivably we could end up with 4 different traces, couldn't we? If we ask, depending on the combinations of the answers to both of those questions. It could be true, false, false, true, 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 and true, false. And that could end up with 4 different outcomes. And so on. So the number of different traces or execution paths we're going to get through the system is given by 2 to the n, where n's the number of times we're going to split, or the number of questions we're going to ask. And so I'm making it sound much more complicated than it is. Does everyone just see? Basically, it's the thing I did about the Martian women and the Martian men and asking yes-no questions. How many questions do you need to ask to be able to categorize something into n groups? And what Claude Shannon would have said is, how many yes-no questions do we need to ask in our program, so our program can select between n factorial possible execution paths. So when will 2 to the, let's suppose we make k choices, 1, 2, 3, up to k, when will 2 to the k, the amount of information we get from querying the data we've got, exceed n factorial? And remember we took logs of both sides and we applied our logarithm rules that are in your textbook now, and we discovered that if we assumed, using Stirling's approximation, that n factorial is approximately, well this isn't even Stirling's, this is more approximate than that, but if we say it's approximately, which you do by just adding lots of lines, it's approximately n to the n, then when we took logs of both sides we found that k equaled n log n, and there's some constants floating around here. And there potentially are lower order terms out there. But essentially, we're going to have to do order big O, n log n, comparisons to be able to distinguish between that many different cases. So, the long and the short of it is, if all we've got in our armory, if as programmers all we can do to change the behavior of our program is to ask questions, is to do tests, is to have ifs and whiles, then we're not going to be able to get away with having less than n log n tests performed. And if we're doing n log n tests, then clearly we're not going to be able to get away with less than n log n work, because each test takes some work. So we've got n log n tests, that means we've got at least n log n work. We could even have more work than that, but we've certainly got to have n log n work in order to be able to do those tests. So that was a barrier we hit. Gee, does that mean we can never sort faster than n log n? What did I say? Colombo. Oh yeah. So I had a way that I think about this, which is every time the program has to, it's like, suppose you're an oracle and the program's asking for help, it's stupid. The computer's asking for help, it's stupid. So every time it sees an if or a while, it has to evaluate some test, it asks you, the oracle, what the answer to that test is. And then depending on the answers you give it, it eventually decides which permutation it has to apply to undo the sort. And that sort of makes me think a little bit of Columbo, if anyone's ever seen it. It's a detective show. And normally there's, say, 8 guest stars in the episode, and one of the 8 is the murderer. And Columbo has to work out who it is. And so what's the minimum number of yes-no questions Columbo's going to have to ask in his investigation? 1. No. No. Sorry. Yes, he could ask, was it you? Yes, it was. Oops. Yeah. No, what I meant is, if he had to do an investigation plan before he went into the old abandoned castle. So he does his investigation plan without actually knowing what the data's like, and he says, I will go in there and I will first ask this question. And then if they answer it that way, I'll ask this question. And if they answer it that way, I'll ask this question. And if they answer it that way, I'll ask, oh, there's only 2 ways for each question. And if they answer this question that way, I'll ask. And he has a big plan of all the things he's going to do. Now, sure, he might go in and the very first thing, first question he asks might lead him exactly to a solution, and he might not have to ask any more. But in his plan, there'll be some times when he's got a pathologically bad sequence of answers, and he has to ask a larger number of questions to zoom it down. So my question is, in the worst case, what's the most questions he's going to have to ask to be sure, no matter what the input data is, that he's going to be able to work out exactly who the murderer is? So if there's 8 people, what's the smallest number of questions he's going to have to ask? 3. He's going to have to ask 3 yes-no questions. Now he doesn't, the reason I picked Columbo, other than the fact I love him dearly, is that he's always going, I'm sure you've all, have you seen, do you even know what Columbo is? You don't? I'm just making it up. He's this great pink fairy detective. He flies around on a broomstick. And I could say anything and you wouldn't even know, would you? It's from another era. So, but anyway, old Columbo always used to say, oh, one more question. And it was really annoying because everyone thought he was an idiot. And then just when they thought they'd got rid of him, he'd turn around the room and go, oh, just one more question. And of course he'd do that because he'd been in his head working out the log of n to the n and thinking, oh, I'm one question short. So this is the way of, this is the way he has to solve murders by narrowing it down amongst the possible cases by asking questions. Why, by the way, do we talk about bits of information? That's why I've said why bits there. Because whenever I talk about the amount of information in something, I'll say it's got so many bits of information. So if I was going to talk about sorting 8 numbers, or a permutation of eight numbers, I'd say 8 numbers is 8 to the 8. Oh no, I can't do that. If I've got a permutation of 3 numbers, 3 to the 3 is 27. So I would say, a permutation of 3 numbers contains approximately how many bits of information? Storing a number between 1 and 27. So how many bits? It's about 5 bits of information. So I wouldn't, because 2 to the 32 is, 2 to the 5 is 32. So I would have to store 5 bits to represent it, and I would talk about the amount of information available there in terms of bits. And Claude Shannon did this in information theory. He always measures the amount of information in something by bits. And I just thought someone might be wondering, why do you measure information in bits? Now maybe it seems more natural to you guys because you're sort of in the computer generation and we talk about bits all the time, but why, if I want to talk about the amount of information in the numbers 1 to 27, why do I say there's 3 bits of information? Why don't I just say there's 27 pieces of information? Why don't I measure the information as 27? Why do I take the log of it? Why do I work out the number of bits to talk about the amount of information in something? And maybe I'll leave that as a little puzzle. Does everyone understand what I'm asking? Why did he eventually, because when you see later on formulas for entropy, there'll be logs everywhere in them. When we work out the amount of information in a particular set of data, we'll be taking logs of things to work out the number of bits. Why bits? Why not just the number itself? Why did we take that extra step where we apply a log? Does anyone want to sort of hazard a guess?
Because computer.
1, then 2.
Isn't it because computer works in binary ways?
Well, computers work, I mean, computers came after Shannon. I mean, in a way, computers don't have to work in binary. They could work in ternary. There's no reason computers work in binary because they store 1 of 2 voltage levels. Well, in the old days, that's how they did it. So the electronics didn't have to be very sensitive to detect if you were storing about 5 volts or about 0 volts. And that way, if the amount it stores, because it's an imperfect machine, fluctuates slightly and it's really storing 4.5 volts, everyone says, oh, it's really storing a 1, that's about 5 volts. And if it's 0.5 volts, they say, oh, it's about 0. So it's very convenient to say we store 1s and 0s because it gives us lots of error correction ability, but there's no reason we couldn't have, and some of the early machines did, store everything in base 3. We could say, oh, well, let's say 0 volts is 1 state, and 5 volts is the 2nd state, and 10 volts is the 3rd state. And that means for every bit, though we wouldn't call it bit then, we'd call it, well, anyway, for every unit of information then, we'd store 1 of 3 possible values. And so on. So why did we pick bits? Because essentially, I've got his answer, but just answering you. So the reason we did bits, the reason computers are in base 2, that was his question, wasn't it? Is that why you're pointing at him?
No, he's the second person.
Oh yeah, no, I'm still answering your question. I'm not going to stop answering your question for hours. It's the best question. I love it. So the fact that computers use base 2 is sort of happened after Shannon, and is sort of because it's convenient to represent information in bits, because it is such a nice way of measuring information. So it's not that computers use bits, hence we talk about bits. It's bits are the right way of going, and hence that's how we design computers, to use bits. So my question is why bits, not other things? Yes, what was your question? Your guess, your hazarded guess to the answer to the question.
Because we assume that for every question we ask, there can only be 2 answers.
Is it because for every question we ask, we can assume there can only be 2 answers? Well, yes, again, I'd sort of answer that in the same way as the first one, that yes, in all languages that I've ever seen, or not all, but in most languages, they only have 2-way choices. And a standard structure in structured programming is a 2-way split. But there's no reason we couldn't have a 3-way. There's no way, I mean, I'm pretty sure on an Intel chip they even give you a 3-way where you compare 2 numbers and it says, is 1 greater than, is 1 less than, or are they equal? And you get 3 execution paths based on the thing. Yeah. In fact, that's such a good question. What's your name? Richard. Oh, what a good name. Such a good... Can you hold on to that question? And when we start talking about trees, can you ask me that question again? because you'll see then why we quite like having a binary split. Why 2 is quite a neat way of doing it. Well, I'm going to leave it as a puzzling question for you to think about, and if I haven't told you by next lecture, which will be actually 2 lectures on from now, what the answer is, why we do measure information in bits, can someone please hassle me to tell them why Shannon decided to measure information using the log of the number of combinations we're considering rather than just the number of combinations? Because it's very interesting. Okay, why do we talk about comparisons? Well, I think I've sort of already answered that. When you're analysing an algorithm, you could analyse our sorts by looking at the number of swaps they did. In fact, we did that briefly for bubble sort. But more or less every other analysis I've done so far, we've talked about the number of comparisons the sort do. Why am I talking about the number of comparisons? What's magic about the number of comparisons? And the answer to that is there's nothing particularly magic about comparisons. And the reason we talk about counting the number of comparisons when we calculate the complexity of functions that are sorting functions is most sorting functions are based on comparisons, and the amount of work they do is proportional to the amount of comparisons they perform. But you could easily invent an algorithm to do something else, multiply 2 numbers, say, that spends hours and hours working and maybe only does 1 or 2 comparisons. And it would be crazy to say the amount of work done by that program would be 2. But here, comparisons are a reasonable proxy for the amount of work because all the extra things you do sort of linearly relate to the number of comparisons we do. After every comparison, we do a constant amount of stuff in a sorting algorithm. Then we do another comparison which involves a constant amount of stuff. Yeah, swap 2 numbers or increase a pointer or something like that. So it's a reasonable proxy, and so it gives us a lower bound on the amount of work the sorting algorithm's got to do, because if it does n log n comparisons, yeah, then it's got to do n log n work at least. So all this is leading to something. I'm not just ranting about information for fun, though it is enormously fun, but it's leading somewhere. Here's something you could do. And we will do as soon as the assignment's handed in. I'm just itchy about writing code at the moment, so I haven't written any sorting code because I don't want to show you any sorting code in case you think that's the code we use in the assignment. I'm just trying to describe all the algorithms abstractly rather than giving you the code for it, so you'll have to write your own code to implement all the sorts. But as soon as the assignment's out of the way, I'll be writing code like a madman possessed. And one of the first things I want to do, and you might want to do it yourself in the meantime, is we could write an instrumented sort. And by that I mean, imagine you write a sort that every time it does a comparison, it updates a number somewhere. So the program itself keeps track of how many comparisons it does. And at the end of sorting all the numbers, it prints a little message out saying, I did 3,917 comparisons. Then it would be interesting if you had such an instrumented sort like that, and then you could have an instrumented bubble sort, and an instrumented quicksort, an instrumented selection sort, an instrumented merge sort, an instrumented, what else have we done? Insertion sort. You could then pump in a whole lot of different cases. So to sort 5 things, there are only 5 factorial ways of arranging 5 things. That's a reasonably small number. Is that 120 or something like that? So to see how many comparisons it does to sort 5 things, you could actually pump in every possible unsorted list of length 5, and you could record for each one how many comparisons it did. And you would find something very interesting, that no matter which sort you did it for, this is the number of comparisons done in the worst case. And suppose we did it for bubble sort and selection sort and insertion sort and quicksort and shell sort, and merge sort, every other sort you want to think of, all the comparison-based sorts. What's the theoretical ideal? The Shannon limit. The smallest number of comparisons we have to do to sort one thing. What's the smallest number of comparisons we have to do to sort 2 things? What's the smallest number of comparisons we have to do to sort 3 things? 2. Who said 2?
I think I see a pattern.
You see a pattern so far? Yes. See a pattern so far. I think Lord Kelvin said something like, give me 3 data points and I can fit an elephant. we need more data points. So for 3, there's 3 factorial, which is 6 possible combinations. Log of 6, log base 2 of 6 is 2 and a bit, to round up 3. We need to do 3 comparisons to distinguish them. 4 factorial is 24, so we're going to need to do 5 comparisons. 5 factorial is 120, so we're going to need to do 7 comparisons. 120 times 6 is 720? Can someone help me? What's that? Is that 10 comparisons? It is, it's near 1,000, isn't it? It's got to be something like 10. And so on. So we keep working out the theoretical amount. Here's the interesting bit. If you ran your sort algorithms and actually counted the number of sorts they did, which was the one I was most excited about, that I was telling you over and over again, this is the best sort ever to use, I love this sort, it's fantastic, which is Quicksort. Quicksort is normally the algorithm of choice. It's hard to get wrong, and on particular machines it runs particularly fast. If we wrote down the number of comparisons Quicksort did, you would find, to your surprise, they're nothing like these. It's the same order of magnitude, it's the same complexity class, but it's doing nothing like the minimum number of sorts. It does a whole lot of extra unnecessary sorts, questions it asks, which is why Columbo episodes sometimes go for 2 hours. You think, come on. You've asked enough, you know the answer now. It's Colonel Murphy with the pipe cleaner in the chimney. Okay, but it just keeps going and going. So our sorts do this. They do these unnecessary comparisons. Shell sort, which I talked about as being interesting, would do way more than the ideal one. Even insertion merge sort, which we really truly love, is going to do more than it needs in the worst case. In fact, none of these general purpose sorting algorithms are ideal or optimal. None of them makes to achieve it. So that sort of begs this really interesting question. Is it that there are sorting algorithms around, a very clever one, that no one's thought of? What's your name? Asan. Asan sort. Maybe we'll be reading about that in 20 years' time. Somewhere there's some mystery sort algorithm that you could write that actually does an optimal number of sorts, or gets very close to it. Well, actually, some of these do get close to it sometimes. It's called the human brain, that's right. Humans can do it, but we haven't come up with an algorithm that can do it.
Yeah, I think we do it like not thinking about it.
Well, I would think humans are very clever. But still, I reckon if a human was sorting, say, 20 things, or even make it more ridiculous, 30 things, without looking, they had the sorting bag on their head, they were just asking, it was comparison-based sort, so they were just asking the guys behind them, are the two, we look, is the item at position 17 bigger than the item at position 2? And the person says yes, and then you ask another question. I bet even the smartest person in the world is going to ask a few unnecessary questions that later on, if we went through analysing, you could say, oh, you could have deduced the answer to question 97 if you'd only looked at the answers to question 16, 12, 52, 18 and 19. They imply the answer, you got a 57. Oh, yeah, of course. So there'll be some unnecessary questions. I think it's just hard. It's a really hard problem. So that's my challenge number 1 to you guys is, can you please invent this algorithm, and can you please call it the Richard sort? Maybe we could do it together. Yeah. Because you guys are have the brains. At the moment, you're like 19, 20. This is the peak of your life. Your brains are the best they'll ever be. Your mathematical ability is at the peak of its ability. You guys are just complete geniuses. You might be lower on knowledge than you will be later on. But in terms of computing power and intelligence and wisdom and insight and creativity, you're at the peak. Next year, washed up. All gone. So yeah, make good use of it. Do invent the Richard sort. So my secondary challenge for you, which is perhaps a bit easier, is can you come up with, I was going to do it in the tute this week, but I didn't put it in. I think I'll put it in next week. Can you actually write customized sorts? Don't try and write a generalized Richard sort. Can you just write Richard sort for 5 items? And work out the questions you'll ask, so you never need to ask more than 7 questions and you always exactly sort it. So a huge nested if statement that's never more than 7 levels deep that will completely sort 5 things. Can we do it? Let's just do it for 1 and 2 just to make sure we can do it. Well, 1 and 2 are trivial. Let's do it for 3. I've got 3 things, A, B and C. What questions would I ask in a huge nested if statement to classify A, B and C into order? To print them out in order. What's the first question I'm going to ask? All right. If A, excuse me, is bigger than C, this is just, we're not going to have enough room, are we? Look at this. This is nice. This is like a list operation. This is very good. Just insert another node. Okay. So if A is greater than C, Then we're going to ask a second question. Just one more question. What is it? Is A bigger than B? So this is yes, A is bigger than C. Yes, A is bigger than B. So we know A is bigger than C and A is bigger than B. Do we have to ask any more questions? Yes. If B is bigger than C, all right. We've asked 3. We're sorting how many things? 3. So I'm hoping we don't have to go deeper than 3. We shouldn't have to by Claude. So can you now print them out in order? What is it? Print CBA in increasing order. Okay. Now let's say else. I hope we can print something out here. Can you tell me something here? Because we're 3 deep again. I can't go any deeper. Cool. All right. So we finished that block. Now let's go else. Did you want to ask another question? Let's write down all the combinations. Let's check we've got them. A, B, C, A, C, B, B, C, A, B, A, C, C, A, B, C, B, A. And which ones have we done so far? We've done CBA and we did BCA. Right, we knocked out 2 of the cases. We've only got 6 cases, and you can see, can't you? Hopefully it's really clear. If we go to, I feel like Harry Potter. If we go to a depth of 3, we're going to end up with 8 possible combinations. Yeah, this is the 2 to the n thing I'm seeing. We're going to end up with 8 print statements, and we only actually have to print out 6 things. So some of those presumably will be things that we never get to. Okay, so what's happening here? This is when A is bigger than C, but A is not bigger than B. We're going to ask the same questions again. Ah, I like this. If B is greater than C, now what does that tell us? A is greater than C, A is less than B, and B is greater than C. Oh, I'm going to have to write that down because this is getting very confusing. A is greater than C, and B is greater, A is greater than C, with greatness goes this way, as it normally does. Greatness is over there. Sorry. We're on the bad side. I can't believe it. Don't worry. Don't worry. Hang on. If we turn round, it's okay. So we've got A is greater than C, and A is less than B. Oh, we don't need to ask any more questions. Who asked this question? Guys, because what do we say now? Print CAB. And else print CAB. Or, I mean, one of those will never get reached. If you, okay, can you see? Keep going like this. We've only got, presumably, a tiny little bit left to go because we've knocked out 3 cases. Or we've got halfway. We're halfway through it now. Can you see you can write a nested if thing to do, to solve it for 3? My question is, can you write a nested if thing to solve it for n, for some non-trivial n? Even if you can do it for 5 or 7, I'll be impressed. But if you can write it for a larger number, I'll be very impressed. Now, this gives me a good opportunity to explain the notion oblivious. You know I've used the word oblivious a few times up till now. Does someone want to try and characterise what oblivious means?
Doesn't know anything.
What's that?
Doesn't know anything.
Doesn't know anything. In everyday English, yeah. In sorting it has a slight, I mean, it's along those lines, had a slightly different connotation. Yeah, Clifford. What's that?
Unaware of its context.
Unaware of its context. What it does is independent of what's happened. So an oblivious person would be someone that, I ask you, what's something I could do that would be oblivious? I could say to you, I've got a plan. My plan is to work out if I'm a boy or a girl. And I've got a series of subtle questions I can ask that'll work it out. And I've worked out the questions. The first one is, am I wearing a dress? And now if they say no, I'm in trouble because I could still be a girl. So the second question is, does my name end with Ina? like Georgina. And if they say no, I say, am I a girl? Okay, so these three questions, this is like a shell definition, isn't it? So these three questions will eventually work it out. So I go, am I wearing a dress? And Clifford says, yes.
That means he's probably a transvestite.
I mean, we can't, well, we don't know. I might just like wearing dresses. I didn't mean to enter that territory at all, actually. I wish I hadn't used this example. It is a kilt. It's a kilt, thank you. So I've now, as a result of my first question, found out everything I needed to know. A clever, adaptive algorithm would now stop. An oblivious algorithm keeps going. Oblivious means it just keeps going. So then I say, does my name end in Ina? No. Am I a girl? Yes. That was an oblivious, that was an oblivious, that's hypothetical me, not real me. So that was an oblivious algorithm. Can you see that? An oblivious algorithm just asks the questions on its plan up front, regardless of what the answers are. An adaptive algorithm, as it gets answers, can change what it does and do clever different things. So an oblivious version of this would ask the same questions at every level, which is what I liked seeing you doing here, because you were coming up with an oblivious way of doing it. You might find oblivious ways can't solve it in optimal moves. You might need to do an adaptive one. But if you can do it oblivious, do it just for the fun of it. Yes?
So like an oblivious one would be something like complete Boolean evaluation. Like if you've got like a human...
Ah, yes, that's a great example. Do you want to say that more clearly, everyone?
Something about complete Boolean evaluation versus short-circuit Boolean evaluation.
Yes. Yes. So just in case you couldn't hear, I just realised I don't have a mic to hold down there for Adam. If C is evaluating this expression, if x is greater than 6 or y is greater than 5, as soon as it knows the answer yes here, any sort of lazy language, or which has what we call short-circuit evaluation, doesn't bother evaluating the rest of the expression because or, if either of them are yes, then the whole thing's yes, so it can just not ask the rest. In a strict language that keeps going right to the end, an oblivious language, now I realise we should call them, it would actually have to evaluate both parts even though it knew the answer part way. That's right. That's an example of the difference between oblivious and non-oblivious. Why am I even talking about it? Because I have mentioned up till now that bubble sort is oblivious. Bubble sort just keeps on going, doing the same tests and swapping, even when everything's all sorted, or even when it knows it won't be doing any swaps for quite a while, it still keeps asking the questions. That's oblivious bubble sort. And bubble sort with an early exit, of course, is the one that stops as soon as it has compared the whole way along and not done a swap at all in a single pass. And that we would call an adaptive bubble sort. So, okay. Quicksort is adaptive. Selection sort, is it adaptive or is it oblivious? Well, these are questions for you. You think about that. That's a very interesting question to ask yourself. Okay, so we've done ideal sorts. I want to do a bit of classification and then we're going to look at some interesting algorithms. Let's classify these complexity sort classes here. Let's classify, did I write down the complexity classes? No, I haven't. Let's classify these numbers and work out, these are the output of some process. Let's have some light. Now I've got this dilemma. I don't have any light. Oh, you can't see it. I'd better turn off the light. So how are we going to solve that problem? Can you see the numbers? Let's just pretend you can see the numbers. That's how I'll solve it. Yes. Because it doesn't really matter exactly what the numbers are. What's more important is what we write on the board here. So, in fact, I'll just transcribe them. You've got some process that of an input of one size puts out 50. You give it an input that's slightly bigger and is 95. Maybe it takes 95 seconds, maybe it uses 95 memory locations. In some sense, this is a function that as the input's getting bigger, we might as well start it at 1, but it could start at anything. Start at 7, I don't care what it starts at. So actually I won't put an index down there, just so you don't think it's important. 184, 323, 518, 775, 11000, 4499, 1499, 1978, very good year.
2543.
2,543, that's a bad year. That's the year that I die. So, I want to talk about that. 3,200. 3955. Optimus Buckland. Oh, I think it's pretty good. If you knew you were going to have that long, that'd be pretty cool. I'll go just before you guys all get cooked. Okay. Looking at those numbers, what are you going to tell me? Is this a linear process? Is this like a quadratic process? Is this an exponential process? Is this n log n? Is this log n? Is this n cubed? Is this n factorial? Is this 2 to the n? Is this 9 to the n? What's the complexity of this? It's O something. O what? Oh, it's numbers. They're all increasing by 1. Maybe it's 1, 2, 3, 4, 5, 6, 7, or 8, 9, 10, 11, 12, 13, 14, 15, or they're just consecutive readings. Maybe we're taking population samples. Maybe this is H1N1 in infestations in a suburb by day.
Exponential it is, but it's sort of doing that.
So you're trying to, so Adam thought we could plot it, first of all. That would be an interesting thing to do. And if we plotted it, it would look like, does it look like that? I don't know, or it could look like this. So you guys, I'm not sure. I don't actually want to plot it. I want you to tell me, plotting's not a bad thing. Plotting would probably indicate it's not linear. How could you work out what the complexity is? There's a range of methods. Let's just see if we can find them. Yeah.
If you compare ratios,
Yes.
you see that it's at least quadratic.
Oh, I like the way you're thinking. How do you compare ratios?
If you assume that you have, let's say, consecutive inputs given an output,
Yes.
you look at 95 over 50, and then you look at 184 over 95,
Yes.
and you can see that it's not linear. It's far bigger than
Okay. So you can check by saying, what do I have to multiply this by to get to here? What do I have to multiply this by to get to here? But actually that's not giving you linear. That's giving you exponential.
it's at least quadratic. You've only got 3 different.
With these three, yeah. Okay. You'd have to show me in more detail later on, but I'm completely convinced that you've worked it out, because you are, in fact, spot on and correct. The ways of solving this, one is take the ratio of successive terms. That's an interesting thing to plot. What's another technique we could adopt in addition to that? Yeah? Cameron, is it? What other method could we use? You were just waving at him. Sorry, I thought you were waving at me. But now you've been picked. You can't escape. I'm oblivious to knowing the answer to that second question. Yep.
What other methods could we use? Besides looking at the ratio.
Yes. Say if this was an exam question. Or say that your boss had these numbers and he said, I'm looking at the spread of this virus. Is it okay? Is it linear? Is it exponential? Is it factorial? What is it? Or I just give you these numbers in the exam and say, what sort of growth rate are we looking at here? What would you try? What methods could you use?
You could assume this include a constant.
Yes.
Start with just like n1 and n2 and see if you can find
Wait.
it.
You could try and solve it. Assume it's a mathematical function and try and solve it for it. Hang on a sec. These might be naturally occurring measurements which might have error in them, or they might have been generated by a formula. So I think like standard ways of solving, what were you going to say?
I still think plotting is easier, but I mean, you can look at it as like a series.
Plotting is a great idea. I didn't mean to poo-poo it. I just didn't really want to do it. That's all, because I'm lazy. But plotting things, your eyes, that's the band. Your ears, that's like dial-up compared to your eyes. So you want to get information into your brain as quickly as possible, send it in through the eyes. And your brain's got dedicated graphic processing units for certain tasks, like it's really good at recognizing faces. So convert this into faces somehow, and you would be able to analyze this so fast. So looking at a picture was always a brilliant thing to do. But suppose I just wanted to do it analytically. I don't want to look at a picture, but you're right, looking at a picture would be cool. Shh, 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 shh. Does anyone have a suggestion for how to do it? A difference table is very good. Who said that? What's your name? Sam. Nice one, Sam. And someone else had something to say? Okay, standard techniques are things like, shh, shh, shh. You could try and fit a curve to it using some sort of crazy mathematical regression package. You could use MATLAB and fool around with that. You could do a chi-square test, some sort of measure of the equality of distributions, and sort of do some sort of goodness of fit test that way. Normally though, in computing, if you have to do a lot of work to tell the difference between two complexity classes, it's not worth doing. You know, they're the same. So normally in computing, all you do is just run it for a bit longer. If it's exponential, it'll explode off the screen. If it's so fine and subtle a distinction that you can't measure it, then what's the point of measuring it and working out the complexity class? But I just wanted to give you some analytical techniques to do it. The way I used was exactly Sam's method. Good on you, Sam. It came from Leibniz, the idea of calculus. If you differentiate a linear function, what do you get? A constant. What happens if you differentiate a quadratic? You get a linear function. What happens if you differentiate a cubic? You get a quadratic. If you just go back to first principles and try expanding it out with all the infinitesimal differences in there, you'll see why that happens. Well, lo and behold, it also works out, as it turns out, for finite differences. So we can use the same method here. If I have a linear function, linear function is 1, 1 is 1, 2 is 4, 3 is 6, 4 is 8. If I take the first differences, I get 3, 2, oh, did I make a mistake there? 2 times 1 is, 2 times 1, 0. Take the difference of these two terms gives me 2, take the difference of these two terms gives me 2, take the difference of 2. Okay. So if I'm getting constants on my first differences, then what I must have been looking at initially must have been a linear thing. Yeah, same as in differentiation. What if I had a quadratic thing? Well, if I take the differences of the differences for a quadratic thing, I'll get constances. I'll get constants, constances. And if it's cubic and so on, so on, so on. So that'll help me identify polynomials. What if it's an exponential? How would I identify that?
Get an exponential, bro.
Yeah, exponentials are harder to, well, a different technique will identify them. Let's just check, can I get everyone, I'm going to point at one person, and as I point at you, you'll be calculating the first difference of these two numbers. And the next person will do the next difference, and the next person will do the next difference. Does that make sense? So if I give the numbers an ordinal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can you do 1 minus 2 minus 1? Write down the answer. 3 minus 2. 4 minus 3. 5 minus 4. 6 minus 5. 7 minus 6. 8 minus 7. You're looking that way. 8 minus 7. 9 minus 8. 10 minus 9. 11 minus 10. 12 minus 11. Okay. Let's call them out. Which one did you do? 4 minus 3 is 139. Any more? 12 minus 11 is 755.
7 minus 6 is 3.
7 minus 6. I'm going to do them in order actually because I reckon you've all got them at the same time. So what's 1 minus 2? 45. No, let him say it. What's 2 minus 3? What's 5 minus 4? 100 and what was it? 195? What's 6 minus 5? What's 7 minus 6? What's 8 minus 7? Whew. What's 9 minus 8? What's 10 minus 9? Thank you, 565. And what's 11 minus 10? 657. I've done it all? Okay. Cool. Are they constant? No way. All right, this side of the room, the greater side of the room. Can you do 2 minus 1 of the next column? 3 minus 2? 4 minus 3? 5 minus 4? Can you do it? No. 5 minus 4? 6 minus 5? No. 6 minus 5? 7 minus 6? 8 minus 7? 9 minus 8? Okay, call them out when you got them. Yeah, it's parallel processing. Oh yeah, this is what sorry, thank you, Theo. The point I wanted to make is, notice we could parallelize everything at the first level here, which gave us an enormous speed up, but the second level depends on the first level. That dependency meant we had to finish the first level before we could do the second level. This is parallelization, the heart of parallelization. What are the dependencies? Whenever you have a dependency, you have to serialize things. You like things that don't have dependencies. Unfortunately, this task has lots of dependencies. Have you guys got the numbers? Call it out. 54? 40? 56?
Third minus second is 89. Therefore, that first one in the third column is 44 and then 25.
Sorry, this is 89. Thank you. This is 44 and 50. Thank you. Okay, 95 minus 257 minus 95, 195? 62. We'll do one more. Everyone else is saved. Sam? One. No. Sorry, this is 325 minus 257. It's going to be something like 68. 68. Okay. How did I know it was going to be 68? Because although these numbers aren't constants, what do you notice about them? So what have we got? What were these numbers initially that we started with? If they were this, it would be linear, quadratic, cubic. So they were cubic numbers. And they were generated by a formula. I cheated. So it's nice. In practice, of course, these numbers are jumping around all over the place. It might be 5, 6, 2, 7, 6. You know, nature is a bit more random than that. But it approximately is stable at that point. Does that make sense? Whew. Long discussion. The reason I wanted to do that, to classify polynomial things, is that next lecture, which will start in nearly 10 minutes, we're going to talk about exponential functions, things that grow faster than polynomials. Okay, go. Have a break, stretch your legs. Oh, I said that last thing was about Leibniz. I did have something to show you during the break. Keep stretching your legs, but let me show you something. Something very beautiful. But break, move around, stretch.
At first I was afraid the answer. It said given this position, find velocity. But I knew that I was wrong. I struggled, I cried, a problem shouldn't take this long. I tried to think, control my nerve. It's evident that speed's tangential to that time position curve. This problem would be mine if I just knew that tangent line, but what to do? Show me a sign. So I thought back to calculus, way back to Newton and to Leibniz and to problems just like this. And just like that, when I had given up all hope, I said nope. There's just one way to find that slope, and so now I will derive, find the derivative of x position with respect to time. It's as easy as can be, just have to take dx dt. I will derive, hey, hey. And then I went ahead to the second part, but as I looked at it, I wasn't quite sure how to start. It was asking for the time at which velocity was at a maximum, and I was thinking, woe is me, but then I thought, this much I know, I've got to find acceleration, set it equal to 0. Now if I only knew what the function was for a, I guess I'm gonna have to solve for it some way. So I thought back to calculus, way back to Newton and to Leibniz and to problems just like this. And just like that, when I had given up all hope, I said nope. There's just one way to find that slope, and so now I will derive, find the derivative of velocity with respect to time. It's as easy as can be, just have to take dv dt. I will derive. So I thought back to calculus, way back to Newton and to Leibniz and to problems just like this. And just like that, when I had given up all hope, I said nope. There's just one way to find that slope, and so now I will derive. Find the derivative of exposition with respect to time. It's as easy as can be, just have to take dx dt. I will derive.